This session involves colligative properties. Colligative properties are properties whose values depend only on the number of solute particles and not on what those particles are. So all of these properties are going to depend on the concentration of the solution, and they're going to have a difference in value between the solution versus the pure substance is going to be related to the attractive forces of our solute particles that are occupying the positions of our solvent molecules. So as these things are mixed together, it's going to affect some of the physical properties that we learned about in previous sessions. One of the properties that is affected by solute particles being dissolved is the vapor pressure. The vapor pressure of a solvent above a solution is going to be lower than the vapor pressure of the solvent if it was pure and didn't have those solute particles. This is because the solute particles are occupying some of that space at the surface, and that can create a bit of an equilibrium that can help keep some of those solvent particles in solution. Sometimes this is referred to as a thirsty solution, and that a concentrated solution will actually draw solvent molecules toward it, making the solution mix and have a reduced vapor pressure. Here we have an equation that you could use to calculate the vapor pressure of a solvent in the solution by comparing it to the vapor pressure of the pure solvent will be related to the mole fraction that we learned about in the previous session. This is not an equation that we're going to be using in this class, but I did want to introduce it here. If the solute is also volatile, meaning that it can evaporate easily, something like alcohol, then that can actually contribute to the vapor pressure and make it higher. So here it shows some examples. So Raoult's law is this law here of what an ideal solution would look like, comparing the vapor pressure of the pure solvent and how it changes as it's in solution. If your solute and solvent like each other a lot, then the vapor pressure will be lowered. If you have a solute and solvent that have weak attractions, then the vapor pressure would actually increase. So this would be if your solute is volatile, the vapor pressure will actually be higher in solution, whereas if your solute is not volatile, the vapor pressure will generally be lower in solution. This can lead to something called vapor pressure lowering, where the liquid region of our phase diagram that we learned about in our previous session will actually expand. So the blue here represents our normal phase diagram with a pure solvent. And when we have a solution where the solute is not trying to evaporate, then that liquid region expands. This means that your melting point will be lower, so you'll have to make it even colder for it to be a solid. And this is something that they utilize when they ice the roads, that those extra ions in the water that they put on the roads helps the ice melt easier because the melting point is at a lower temperature. And then it also increases our boiling point range, that you'll have to heat it up more in order to get something that has solute particles dissolved in it to boil. Here we have some equations, and these are actually the same equation, just this one is based on boiling, and this one is based on freezing, that you can use to calculate how the temperature changes based on the molality of your solution. Now, the equation in your textbook doesn't start by including this I value, which is called the Van 't Hoff factor. This is the ratio of moles of solute particles to moles of formula units that are dissolved. The equation they start with in the book does not include this value because if you have a non-electrolyte, something that is not ionic, then this I value would be 1 because non-electrolytes do not break down further when they're in solution. But this I is an important thing to include whenever you have something that's an ionic solute, because the ionic solutes will break apart in solution, making more ions, and more ions end up being more particles, and more particles mean these colligative properties are impacted more dramatically. The other part of this equation are our big K constant. And so here there is a table that includes our constants, that Kf is how the temperature changes for freezing, and Kb is how the temperature changes for boiling. Now, when we apply these equations, these are the change to the temperatures. So for boiling point, since the boiling point is increasing, you will add the delta TB to the normal boiling point. And for freezing, since the freezing point is lowered, you will subtract the delta TF from the normal freezing point. So the freezing points will become lower and colder. The boiling points will become higher and hotter. So here we have some examples of different solvents. So you definitely do not need to memorize any of these values. However, it's helpful to know the values for water, where the normal freezing point of water is 0 degrees Celsius and the normal boiling point of water is 100 degrees Celsius. But any of these other constants will be provided, or you have permission to look them up. So now we can switch over and do some examples applying these equations.
So this first example is on freezing point depression. So that means that we are going to lower our freezing point. So we're looking to find, so depression. Oops. So depression means that we are lowering the freezing point. Okay. So we're trying to calculate the freezing point of a 1.7, and this italic M is molality. That's what we need in our equation. So this equation is missing the I that I had included in my equation. So ethylene glycol, since that's not something that we know how to write the formula for yet, we do see that it's not something that has a metal in it, so it's not ionic. So anything that's not ionic is a non-electrolyte, which means that the I is equal to 1. So that's why it's not included in this equation. So here we're finding the change in the freezing point. So we have our I would be 1. Our molality is given as 1.7 molal. We have our K value, or aqueous, means that our solvent is water. And knowing that the solvent is water is how they were able to look up the Kf value in that table. So then they calculate, this is the change to the freezing point. So since we're lowering the freezing point, we have our Tf, our freezing point for normal is 0 degrees, minus our delta Tf that we calculated, 3.2 Celsius. So that's how we get negative 3.2 Celsius as our new freezing point. So we've lowered the freezing point of our water by adding some solute, some ethylene glycol. Okay, so here we have another example where again we're asked to calculate the freezing point. We are given the molality. We are given that it's aqueous, so this is water is our solvent. And we're trying to find the freezing point. So the Kf that goes with water, F because we're looking at freezing point, is 1.86 degrees Celsius per mole. And since it's sucrose, that's a type of sugar, so that's a non-electrolyte again. And if it's a non-electrolyte, then the I is equal to 1. So our delta T for our freezing point is going to be our I times our Kf times our molality. So our I is 1, our Kf is 1.86 Celsius per molality, and the molality is given here, 2.6. So we plug that in and we get 4.8 degrees Celsius. But we're trying to find the actual freezing point. So our TF new is going to be our normal freezing point for water, which is 0 degrees Celsius, minus our delta T, because freezing point makes our adding solute makes our freezing point go down. So that's why we're subtracting. So it'd be negative 4.8 degrees Celsius. So this is asking, instead of asking for the new boiling point, this is asking what mass of ethylene glycol in grams must be added. So we're trying to find the mass of the solute. That's our goal. Must be added to 1 kilogram of water. So here's our kilogram solvent to produce a solution that boils at 105 degrees Celsius. So this is our TB new. So water is our solvent. Ethylene glycol is another non-electrolyte, so our I is going to equal 1. So we have an equation that relates our change in boiling point to the molality times our Kb and our I. And we are trying to find out about the mass of the solute. But molality is the moles of solute per kilogram solvent. So we can use this equation to find the molality, and then we're given the mass of the solvent, so we can use that to find the moles of the solute, and that's why we will end up needing the molar mass from the periodic table, so that we can connect the moles of solute to the mass of solute, because that's our goal unit, is to find the mass of the solute. This is where we're using those problem-solving skills of picking apart what information we're given and seeing how we can connect it to the units and goal units that we want. So here they went ahead and solved the equation to find the molality. The delta TB they found because we have 105.0 Celsius was our new boiling point, minus 100 degrees Celsius is our normal boiling point, TB normal. So that's how they found 5.0 degrees Celsius is our delta TB. That's how they found that they plugged in here. And they divided it, the KB would be a constant that they looked up. So here they found the molality. That italic M is molality. Then they used the molality as a conversion factor because we know the mass of the solvent. So we use that to find the moles of the solute, and then we use the molar mass to convert our moles of solute into mass of solute, which is our goal unit. This example is a little bit more similar to the other ones that we did, except it's still for boiling point. So here we are given the molality Aqueous means that our solvent is water. Sucrose is our solute, and then it's a non-electrolyte. It's not ionic. So that means the I value will equal 1. And we are trying to calculate the boiling point. So we can use our delta T. Since we're looking for boiling point, it'll be TB is I times the KB times the molality. And the KB for water would either be given, or you'd look it up, is 0.512 degrees Celsius per molality. So we can find our change in boiling point. So our I is 1, our KB is 0.512, and then the molality is given as 3.60. So those units cancel. And our delta TB is 1.8 degrees Celsius. So our TB new will equal our normal boiling point. So for water, that's 100 Celsius, plus our delta T, because adding solute makes the boiling point go up as long as it's non-volatile, like sugar or salt. If we added alcohol, then that would make the boiling point go down, because alcohol boils easier than water. So this is 101.8 degrees Celsius. So that would be our new boiling point after we have added the sucrose. If you have something that's ionic, like calcium chloride, the I will not equal 1. So now, based on what we know, we expect the I value for calcium chloride to be 3, because calcium chloride, if we break that into ions, is 1 calcium ion and 2 chlorine ions. But that's based off ideal if everything breaks apart perfectly. In reality, I's are not always exactly whole numbers. So we could do a calculation to find out exactly what the I value would be. And so that's over here. We're doing our calculation where we actually measured the freezing point of our solution and are calculating the value of I. So when we do that, since our freezing point was negative 0.27, that means that our, TF normal for water is 0.00 degrees Celsius. So if our TF new is negative 0.27 degrees Celsius, that means that our delta TF is 0.27 degrees Celsius. So that's how they got this value. They rearranged the equation to solve I. The KF is known because our water is solvent. Our solvent is water. So that's how they know the KF value. And so we can see when we calculate it, it's 2.9, which is very close to our expected I equals 3. So for your calculations, you can always assume that I is the expected value. That this example is just to show you that it is not always, in reality, exactly equal to the expected value. Okay. So here we can do one more example, calculate the freezing point of an aqueous solution. So that means that water is our solvent. We're given the molality and we're given our solution. So FeCl3, if we break that into ions, we have 1 iron ion and 3 chloride ions. So we'll use an I equals 4. So our delta TF, because we're looking at freezing, is going to be I times the molality times the Kf. So our I we said was 4. We're making 4 ions. The molality is given at 0.10. And then the Kf for water again is 1.86 degrees Celsius per mole. So the molalities cancel. And our delta T is 0.74 degrees Celsius. But we need to know the actual freezing point. So our TF new, now that we've added the solute, is going to be our normal freezing point for water is 0 degrees Celsius. And the freezing point gets lower, so we'll subtract our delta T to get negative 0.74 degrees Celsius. As part of the way, when they do salt the roads in winter, they don't use sodium chloride. They use a salt that makes more ions. They also use a salt that tends to be a little exothermic when it dissolves. So that allows it to help melt the ice even more.
So those were some examples using our equations for changing boiling points and freezing points. The other parts of this chapter are going to be more qualitative, of just learning some terms. So some terms important to this chapter include osmosis, which is introduced in this chapter, but I also bring up diffusion because these are two things that people get confused a lot. So osmosis is when the solvent flows from a solution of low concentration into a solution of high concentration. So this is where the solvent moves in order to help dilute something that's concentrated. We can use this by separating solutions using a semi-permeable membrane that allows solvent but not solute to flow through it. This is where we can get something called osmotic pressure, where there is pressure needed to keep that osmotic flow from taking place, to keep that solvent from moving. You may have heard of a technique called reverse osmosis purification, and that's where they use this osmotic pressure to push the solvent in the reverse direction in order to purify the solvent. Diffusion is where the solute flows from a solution of high concentration into a solution of low concentration. So you can see how these terms might get confused very easily because they both result in something becoming diluted, but the difference is in which part is moving. So osmosis is when the solvent flows, diffusion is when the solute flows. So you may have heard the joke where people say they're going to sleep on their book to learn by osmosis, but that is not what we actually want, because osmosis would mean that the solvent is moving. So if you're sleeping on your textbook, the osmosis would be if you drool on your textbook, where the solvent dilutes the high concentration of knowledge. So what you actually want would be diffusion, where you want the knowledge, the solute, to flow from the textbook to your brain. So hopefully that can help you remember the difference between these two terms that are often confused. The other part of this session deals with some other types of mixtures. We can have suspensions. These are heterogeneous, meaning that they have visible chunky parts or visible parts that are not consistent. And these types of solutions will separate when they're standing. We see a lot of this with some salad dressings that will separate, so you have to shake them up in order to get them to mix again. Another type of mixture is called a colloid. These are also heterogeneous, but the particles are small enough that they don't separate when they're standing. So this means that the particles can coagulate, but they cannot pass through a semi-permeable membrane. They show something called a Tyndall effect, which is where the particles will reflect light if you shine light through them and create an effect where you can actually sort of see the particles. Over here are some examples of different types of colloids that can help you understand what's happening. So we can have different kinds of solutes and solvents mixed together, but they all will have that kind of reflection effect, like fog, smoke, whipped cream, milk, opal. Toothpaste is another common example of something that's a colloid. Another important thing for this chapter is where we can have things that are both polar and nonpolar and how those can work and create emulsions. So soap is a fatty acid salt that forms a colloid because of that unique structure, where part of it is long and nonpolar, so that part will be good for attracting to nonpolar fats. And then the other part is either polar or ionic, which can be attracted to polar things like water. This is what allows soap to attract fatty particles off your hands or clothes and dissolve them in the water, which is attracted to the polar or ionic portion. This is where we have something called hydrophilic, which means it does like water, and hydrophobic, which means it does not like water. This structure allows the oil to form these little balls where all the nonpolar fatty stuff is in the middle, and then it forms a barrier around the outside of this ball that allows it to be attracted and swept away by water. These balls are called micelles, and this process that allows these fat particles to get carried away in a polar fluid is called emulsification. So hopefully our last session of new material was helpful for you.